All right, so we're going to finish up the optical track with a panel discussion. And if you see your name on the slide, please come to the podium. Um, and there are microphones. I think there's 3 microphones which are handheld. And Ellen, I assume you're getting mic'd up. Or did they mic you down now? Okay, all right. So while the panelists are getting ready for discussion, I do have a few slides that I wanted to share. Of course, the first slide is a forecast because, it's a light counting slide. So the market is doing very well for the last 2 years. It's been growing like crazy, and some companies are slower, some companies are faster, but when we do the forecasting exercise, we model each one of the top 10 companies separately now, individually, in terms of the consumption of optics. All these curves come mostly from the top 3 cloud vendors. I think Andy mentioned that 90% of kind of high-end optics going into the top 3 cloud companies. Yes. I think this year it's more like 100% of the high-end optics going there. By the end of the forecast, it will change, so it may decline to like 80, 70%. I don't remember off the top of my head at the moment, but you see 200 gig doing very well this year thanks to Meta. 400 gig, we have 2 flavors, one deployed in Google, the other one at Amazon. That market is a bit slower this year. We expect to see more in 2023. Of course, if we do go into economic recession, it's going to be hard to stay completely immune to that, so it may slow down. We're not in the business of forecasting economic recessions. It's a hopeless exercise. So we're looking at kind of a longer-term picture and modeling our numbers using assumptions on the traffic growth in those data centers, which is doubling every 2 years. We're assuming it's going to stay at about the same rate. In fact, what we see in the front end of the networks, the traffic growth is slowing down to probably 30%. But the back end, which runs all the AI and machine learning application, traffic is growing much faster. So those 2 sides of the network kind of averaging down to about 40% per year, which an assumption that worked reasonably well for the last 3-4 years for our forecasts. So since we don't know any better, we'll continue forecasting with the same approach. So, we're getting to the numbers which are fairly decent. So you see unit shipments getting to above 10 million for 400 gig, and I think 800 gig is going to be projected to get there by 2027. 1.6 terabit is also very much on the map. One of my questions to the panel will be, are we going to really need 200 gig SerDes to get to 800 and 1.6 T optics? But before I get to the question, I have 2 more slides. And co-packaged optics versus transceivers, we've been arguing about it for quite some time. Light counting loves new technologies, but we also know that it always takes longer for new technologies to penetrate the market. So we're fairly conservative on our assumptions. So we think that by 2027, maybe CPO can take 10% of the market from transceivers, and in this case, we're looking at 1.6 T transceivers specifically. The slide on the right shows our segmentation of CPO deployments by application. So we think that AI clusters and HPCs will be the primary destination for CPO. It could be co-packaged with switches, whether it's Ethernet, NVLink, we don't know for sure. We may see co-packaging with GPUs as well. We feel that the demand for bandwidth in AI clusters, HPC, is significantly higher. It's certainly growing faster than anywhere else. Companies will have to take more risk to stay up with the traffic growth. So I think the barriers for entry are a bit lower at AI clusters and HPCs. I think the argument who's going to win co-packaged transceivers is a wrong argument to have. I think both technologies will have a play. And when we do our forecasting, we start with what we know. We know the market for transceivers. We know the market for cables, not only optical cables. We also forecast active electronic cables and DACs. So we look at the market as sort of a transition from what we know to the future. And CPO will take a share of AOCs, DACs. It will take a share of transceivers. However, I have to admit that we're missing potentially even larger side of the market that we just don't know enough about to be able to forecast it and have enough courage to present the forecast to communities that does respect light counting a little bit. So we are learning about new types of interfaces that we know very little about. And these are die-to-die interfaces that I think Alan mentioned in his presentation. So there are some NVIDIA interfaces, there are several others. I have to admit, I know very little about what these are. What matters for me on that table is the energy per bit. And that's about, well below 1 picojoule per bit. So my message to the community is that CPO will happen in its own way. Transceivers will continue to sell. Both approaches will have an issue of moving beyond even 1 picojoule per bit energy consumption target to really help the industry and to open much larger market for both technologies in the future. So it's hard to learn new things, but we're trying to learn more about this market, and actually Rob was the one who encouraged us to go and study it about a year ago. We're just finally getting to it. So I think this is my last slide. So I have a list of seed questions to start a discussion, and then we're going to open it up to the audience. So I think my first question is to Andy, and it's not about CPO. It's just about...
I'd love to talk about CPU.
No. We're not going to let you. We know what you're going to say. So the question is, 200 gig optics and 200 gig SerDes. What's your view on, 200 gig optics kind of already exists. Are we going to really need 200 gig SerDes in the next 5 years?
Well, that gets down to the chip density and getting the I/O off the chip, right? So it's generally believed that 512 lanes per chip is pretty much the limit, which at 100 gig is a 51.2T. If you want to go to 1024, you really don't have a choice. You have to go to 200 gig SerDes, which go hand in hand with 200 gig lambda optics. You don't want to have a gearbox to go back down to 100 gig at that point. So one of the drivers for the 200 gig lambda is the 200 gig SerDes. The other one is just the expected cost reduction.
Right. So one of my former colleagues who retired a couple of years ago, and he's a good friend of yours, Dale Murray, he was always telling me that, the switching ASICs cannot go beyond 256 ports. And now we're at 512. Is it going to be, what is limiting that? Can we still go beyond?
It's limited by the package size, right? So the 512 512 channel chips have about a 90 by 90 millimeter package, and the limit is pretty much 100 by 100. So we're very close to the limit of what conventional package sizes can be.
All right. So my next question is to Rob and Craig, and I think we're going to start with Rob, actually, and then follow with Craig. Both of you mentioned it in your presentation, but I would like to give you another opportunity to build a case for co-packaged optics and your view of kind of the long-term evolution of this technology.
Okay, so I think at a high level, the way I think about it is this, which is if you follow what's happening in this, it's all driven by the ASIC, right? So if you follow what's happening with the CMOS world, because of the end of Dennard scaling, power densities are going up, which is going to force us to disaggregate chips. Right now, you can disaggregate chips in a multi-chip module and still build something which is reasonably powerful and coolable. But over time, we're going to have to move those chips further apart to continue to be able to power them and cool them. and I need a longer distance interface to do that. I can't do it electrically because of the amount of bandwidth I have to move, so I have to pivot to optics to enable continued system growth and continued system scaling. So I think long-winded answer to your question is, it's kind of an inevitability that we have to do this. The question is, I think you touched on this in your lead-in, which is when and what are the barriers to entry, and when do we get comfortable with the technology to be able to adopt it at the scale we need it?
Right. Craig?
I agree with everything Rob just said. I think this is a journey that sort of we can predict where it ends. The question is, how many steps does it take to get there? So for us, first of all, we've already made the decision to move to 200 gig SerDes in the next generation. We do have the luxury of being able to do that without a broader ecosystem around it with InfiniBand and NVLink granted. We will explore both front pluggable and CPO options in the next generation. It's not clear until you build it and build it at scale what the problems will be. So we're not betting the farm on CPO. We will explore it. I think that the issues will become clearer once we have that built out at scale, and we can make decisions on is this 1 generation away, 2 generations away. But I think agree with Rob. This is sort of going to an inevitable endpoint.
Right. So, Craig, one of your slides, I think it was your last slide, that you mentioned that you focus a lot of your kind of development effort on lasers themselves and modulators to get to the energy levels that you like. I think Alan had, 0.3 picojoule or something as your target. So, is that the type of technologies you're looking at?
Yeah, that's right. I mean, I think what Alan and Quintessent are doing is really interesting, and sort of where we need to get to. Like, to be very clear, we work with a broad range of technology partners. We're exploring multiple pathways, but certainly reducing loss in the silicon chip, getting a much more efficient laser source to match with a low loss silicon chip are absolutely necessary for this sort of integration to happen. Until then, you're kind of just pushing, milliwatts around.
Right. So, Alan, a question to you. I mean, a fascinating technology, but it's hard to push it into the market if you are a single startup developing it. Do you see a kind of an ecosystem of startups building around those future opportunities for really low power connectivity?
Yeah, that's a good point. And I reflect on this a little bit in my ECOG reflections to Gazettabyte, but from my vantage point, there's us, there's other companies, IR Labs, Avicenna's tackling it from a different perspective, and other folks also. If we kind of just restrict our focus to high wavelength count solutions, there's a number of startups kind of starting to coalesce around the ecosystem. And I think there's definitely interest in sort of, trying to standardize and kind of come together to increase the size of the pie and see the market, if you will. So, Chris is leading the CWWDM MSA to standardize the interface for the laser sources. I think there's interest in kind of expanding that to the link level. Yeah, I think that's going to be a necessary step to kind of broaden the market.
Right. So one last question that I had in my notes is optical switching. Google disclosed their experience over the last decade of using optical switches, circuit switches, in their facilities. What is your opinion about this technology? Do you think it will find application in your systems of the future? Craig, we'll start with you.
All right. As you mentioned, I think Google sort of lifted the veil on where they saw value in deploying OCS. We haven't deployed OCS in any significant way yet. We've looked at it. I think that obviously where there are deterministic, predictable traffic patterns, it could make sense. Our motivation to look at optical switching would be to help with resource provisioning in large scale heterogeneous systems. It's certainly not a replacement for an EPS, a packet switch. It would be an additional layer. And it has to provide value.
Right. Andy, what's your opinion?
Google published their white paper on why they did it and how they did it, but I will say it's a very unique use case, and we haven't seen that deployed anywhere else in the cloud. And they did their own, vertical software stack integration to have an SDN functionality that would rearrange these optical switches the way it made sense for them. It worked for them. It's certainly an interesting demo, but it is fairly unique, I would say.
Mm-hmm. Well, we've heard that Berkeley team is running their supercomputer and they're looking at implementing optical switching, or maybe even they already tested a few
but that's a different use case again. One always has to look at exactly the use case you're trying to solve, right? Traditionally, optical switching was used for layer 1 failover, basically, right? Redundant links and so on, or in manufacturing tests, things like that.
Right.
It's very unusual to see it in a production large-scale, high-scale network.
Okay. Rob, what do you think?
So I think today it could be used pretty efficiently for improvement of operational challenges that you have in a data center, like rewiring a data center for a different topology. But based on the speed and the radix of available optical switches today, I think I agree with what Craig said, which is it's not a replacement for electrical switching. It can be used in concert with it to relieve some pressure in other areas of the network. Right. Or if you wanted to reconfigure your cluster, reconfigure the compute fabric to serve a different job, but it would be something that you would do ahead of job runtime. It wouldn't be something you would be reconfiguring on the fly as your compute job would be running. It's more of an operational nicety at this point, I think.
Right. Alan, do you think you can add a little optical switch next to all your micro rings? You have so much stuff there. Just one more is not going to make much of a difference.
I have two comments. I mean, first of all, I want to echo what Craig and Rob said, which is, I don't think it's ever going to be a direct replacement of electrical switches. Just making the observation that optical switches don't have memory, right? So you can't do any buffering.
Right.
And then, in response to your question, I'll give an answer to a different question, which is if there's going to be an optical switch in the link, we can enable that with our integrated amplifiers or a higher budget.
Right. Good point. All right, we're going to open up for questions from the audience, so please use the mics on both sides. Go ahead.
Thank you for everyone. Everyone had a great talks. The question I had was regarding AI and ML. And if that should be an open interface, like for example, how NVIDIA is building their DGX and their SuperPod, it's really a fully proprietary, and the question is that, is it really that different than how we build Ethernet? It's not. As like what Greg was saying, they're building like a 2-stage and 3-stage, and but it's all sort of monolithically built. So if that's the case, should the O there be changed to a C instead of an O? So I just wanted to see, if AI and ML become so prevalent, do we need to have a network that is open rather than a network that's proprietary?
Well, I mean, first of all, it's already prevalent and it's already open. We at NVIDIA, we sell at all levels of the supply chain.
Right.
So we sell a single GPU, we'll sell a tray of GPUs, we'll sell a complete server, and we'll sell you a complete cluster.
Right.
And many of our customers will take GPU trays and they will add their own network interfaces and deploy clusters in their own flavor. So that's what happens mostly today. What we tend to do, and where we lead with InfiniBand and technologies like NVLink, is really to show how far you can push the technology, what can be done if there are no constraints, and and we try and do that in a way that is that utilizes as much of the ecosystem and supply chain that exists today.
Right. What I meant was that should you possibly bring like NVLink into the OCP as an open standard, or is that something? Because I mean, ultimately, I think because if you think about it, if you want to have a common AI ML, and your system is probably the most common, and moving forward, looks like you're going to migrate from probably Ethernet and InfiniBand to more like NVLink in networking. Is there a new? I think it's called quantum switch, or
Yeah. So we offer the customer choice.
Right.
We in fact most of the accelerated or supercomputer deployments today are done on Ethernet. We recognize that. We have a line of Ethernet-based products as well. Again, InfiniBand and NVLink, we do these for specific reasons to show what can be done.
Right.
The question of whether that ever gets opened up, I will never say never, but the reason we don't open those up is because we're not finished developing them yet. And there's more work to be done before that becomes, ready for, openness, if you will.
Thank you.
Maybe I'll throw a partial lifeline to Craig. Didn't NVIDIA announce that the NVLink chip-to-chip standard was going to be open to third-party chiplets?
Yes, that is correct. So we are starting to, there is a sort of a crack in the door there, so to speak. And that's basically the you see here the high bandwidth interface that we utilize between the Grace and Hopper GPU as well as Grace to Grace. This was all announced publicly, in the last year. So that we will start to work with key partners to enable that interface on other devices that can connect to our chips.
If I could add one comment here, it takes a while to create a standard, quite frankly. So like Intel UCIe, which was published or first announced earlier this year, I believe, right, is still in the formation stage and finalization stage. And by the time there's really products on this, it literally takes years, from let's do it until it's really available as a mass product. So one has to look at the use cases for each of these optical chiplets that are associated with these standards. And UCIe addresses a certain use case, and it's a large potential use case. It'll almost certainly take off, right? Whereas it's not the same as the NVIDIA chiplet or some future, next generation high performance thing that's double the speed yet. So it's a little, I don't know the right word here. The technology is evolving fairly quickly in this space, and it's almost hard to pick one target and saying that's the answer to all questions. Whereas in 2 years from now, you would have picked a different target, right? And this is partly because it's hard to, one vendor can define it and ship it for 2 years, but then they would do something else 2 years later. So in very high-speed moving environments, it's harder to do. Whereas if you compare this to Ethernet, Ethernet standards have been around for, I don't know, so many years I can't even remember. But the Ethernet is sort of the opposite of that, except for this transition from 112 gig to 224 gig, which is well understood. There's nothing else really happening there that is comparable to what you could do in chiplets for the next generation GPU. And so one has to look at these use cases, I think, for each category separately.
Rob, do you want to add anything?
No, I mean, I think I agree with everything everybody said, right? I mean, standardization and opening things up takes time. This whole sector, this whole market is moving at very high velocity, and we can't afford for it to slow down. One thing I would acknowledge is that in the realm of AI ML, we're also doing hardware-software co-design. So that adds another layer of complexity that needs to be comprehended end-to-end holistically. So I think in time, yes, things will become more open and more open sourced in nature, which is perfect for OCP discussion. But I think it's still very early in the overall maturity of this technology.
Right. Any more questions from the audience? Go ahead.
If I could add just
Question from
one more
the
thing here, which is,
panelists.
together with standardization, one needs economics, right? So any of these things are only interesting once you get to, I don't know, 100,000s, if not millions of units. So the markets that are being addressed by these use cases have to be big enough to justify the investment of not just perhaps one vendor, but if it's an ecosystem of multiple vendors. So usually the ecosystem develops once the market is more proven in terms of the volume, because otherwise the risk of entering is very high. And a lot of money has been invested in previous efforts that didn't yield any results. And as a startup, you can't really afford that. So it is something where you almost want a proven market that is stable, and then more vendors will join the bandwagon. So,
Right.
so many words.
Right. So actually, that reminds me, I forgot to make a point that, we're talking about high volumes of transceivers, 10 millions of units per year. Yes, for the optics, it's a high volume, but as Scott mentioned in his presentation, he doesn't know exactly how many wafers they use, but it's probably not as many CMOS wafers that required to produce all this technology. I actually did an exercise, I think it was 5 years ago, to calculate how many CMOS wafers it will take to support the whole market. I think it was less than 100.
It's not limited by the supply chain.
Right. Right, but the point I'm getting, I was reading an interesting article on the plane here that was talking about, I think it was one of the startups developing some new optical switching technology, but they were talking about the number of connections in human brain, or synapses, as they call it, 100 trillion connections. So we're talking about here 10 million units of transceivers.
But the analogy to the connections is the size of the parameters in the data sets, right? Where you have hundreds of billions of data sets today. So
right.
It's not the optics, it's the size of the data set in memory.
Right. Well, but still, the point I was trying to make is that, those volumes of 10 million, we're probably going to be laughing at 10 years from now if we get to that sort of die-to-die connectivity.
But on your point of it, can you go back to the previous slides? Sure. The thing about the Ethernet market is it's well understood how big it is. This represents billions and billions of dollars of revenue, whereas the optical chiplet market is just at the very beginning, and the expectation is it's much lower cost per bit. So here you have to get to millions to be interesting, right? And I think it will get there, but it's a much more demanding economical curve.
Right. So I guess in order for companies like Quintessent to be able to raise money, we'll have to put a dollar mark on that forecast for CPU.
We point to your charts, our pitch decks.
We don't have any dollar marks here. It's all units. So we'll have to create we have it in the report. That's true. Any more questions from the audience? So we have a couple. Go ahead.
Vlad, is it okay if I ask more of a networking-oriented than optics, or is this optics?
Go ahead. It's an OCP. You can talk about anything.
Thank you. So in Alexa's presentation, she talked about the need for large-scale networks and how to deal with reducing tail latency in machine learning. And then Ram came out and showed this guy that he hired from some PhD from London and his approach. The Cisco guy came up here, showed his approach with queuing. Andy, particularly, I'm really curious your thoughts on where the network's going to go for large-scale AI to reduce tail latency.
Yeah, that's a very interesting topic. It's not directly related to optics, but in 1 minute here, there's been a lot of simulation work being done recently that did point out that conventional Ethernets have these queuing effects, which are also present in InfiniBand, by the way. But the nature is that if two things want to go to one port, they queue up, right? And if you have a lot of these things ending up in one thing, you get head-of-line blocking, or in InfiniBand would be the congestion algorithm that would push it backwards. What you really want is a virtual output queuing network for the whole thing, like 10,000s of nodes, where it's at the edge, so you only get into the network if you know you can deliver that packet. And there are experiments, there's simulation work that has shown that this is very effective, and you can load these things up to very high utilization without pushing up this latency, which everybody hates. So the average latency in a VOQ system is actually superior to the traditional closed networks at scale. It's just nobody has really built this yet, but there's a lot of interest in this particular direction.
Go ahead.
Hi, Vlad. I wanted to answer your question to help out Alan. I'm here on his nickel, so I do want to help him out. you mentioned that technology is niche, but actually there's many companies that are developing DWDM, multi-wavelength technology. And he was missing a call to action chart. I don't know if it's call to action only for OCP, but a number of companies are actually going to work together to go into UCIe and try to standardize an optical interface there. And to Andy's point, it's going to take us years, so we're under no illusions. You know, it's a chicken and egg thing. There is no multi-wavelength technology, so you can't have an application that's based on it. On the other hand, until you have some kind of an ecosystem, you're not going to have those applications. But in fact, as a call to action, I talked to a number of people at ECOC, and there's a number of companies very seriously interested in it. And if there's others, please join us, and we'll try to actually get some standards in place for the links, not just for the laser sources. Thank you.
I see. On a related subject, I had discussions with OCP management on creating a new initiative within OCP next year, specifically to promote development of new technologies, not necessarily standardizing them to start with, just let them develop, let's see what they can deliver, but help them to find customers, help customers to be aware, potential customers to be aware of these developments. So I think that's something that OCP will be launching next year. I don't want to pre-announce it too early. I think they have to get it done right. Andy, you want to add something?
Yeah, I want to make another comment on economics here, which is what's true about the Ethernet standards is they were originally written for DML, EML, you know, VCSELs. I mean, there was like 10 different things people tried to accommodate in one standard, and that's what they are, and nobody's going to change it. If you started with a clean sheet today, you wouldn't build an optic standard similar to the Ethernet one. You would do it with narrow spacing, like, you know, the work that was here presented here, and it would be far lower cost per bit because you can do much denser integration with lower power and low components. So there is a case that the Ethernet standards are limiting the advance of the lowest potential cost and power direction, and I think that by itself will create a space for chiplets that do this more effectively.
Right. So I think it's probably the right point for the industry to kind of pause and take a look at a broader range of technologies before committing for, you know, the existing technologies for next decade.
Having said that, you still need volume, right? So.
Well, yes.
Yeah, I mean, I couldn't agree with you more. I think, you know, we will take the opportunity to look at this from a blank sheet of paper for the next couple of generations, because we have to. I will say, though, and I made this point earlier, that we made a conscious decision to deploy optics, even for InfiniBand and NVLink, that utilize the same PMDs, the same chipsets, the same components that we used in the Ethernet ecosystem. And that was a very conscious decision because of the economics and the volume that Andy talked about. And the thing that keeps me up more than anything else right now is supply and being able to ramp these 800 gig modules into anywhere near the same sorts of volumes that 100 gig 4x25 has been shipping for years now, and that's a bigger short-term issue than anything else.
And yet, in one of your slides, you mentioned that NVLinks may go faster than Ethernet, so you will be diverging from the supply chain.
Well, you know, so there's a number of ways that you can achieve, you know, higher bandwidth per link, say. But again, I think, you know, when we look at a new technology to deploy in the next generation interface, one of probably the most important criteria for us is, can this be scaled? Can this be ramped into high volume? Mm-hmm. You know, nothing else comes close.
Right. Okay, Chris, do you have another question?
I think I heard Andy volunteering to join our effort to do smart standardization of lower cost optics. So we'll add you to the list.
I'm always in favor of standards.
All right. Any last comments from the panelists? Any topics that I should have asked a question about. I think we exhausted the list. It's been a wonderful afternoon for the first performance of the optical track. Andy, I know you have some closing statements.
I just want to remind people, all the presentations will be available on the OCP website shortly after this conference ends. So if you wanted to see all the slides and even I think the video recordings, they will be all on the website. Thank you.
All right, very good. But Andy, in the program, you're supposed to give us a closing statement.
I think this was of great interest to this topic, so we hope we do this again a year from now.
That's it. It's supposed to be 5-minute statement. All right, well, I'm just kidding. Thank you, Andy. Thank you, Rob, Craig, Alan. And thank you for all of you for joining the panel. We'll do it again next year.